good evening, whatever the case may be, depending on where you are located. My name is Mark Berkmo. I'm a Regional Sales Director for Men&Mice, located here in Michigan in the U.S. And welcome to today's webinar entitled DNS Fragmentation Attacks, the Dangers of Not Validating DNSSEC. During the webinar, all attendees will be in listen-only mode, but please feel free during the webinar to use the chat function to ask questions that will be answered during the question and answer period at the end of today's session. We will be recording this session, so if you find that it is something that you would like to watch again or share with your team, you will have that option shortly after the webinar has concluded. With that being said, I would like to introduce today's distinguished speaker. Mr. Karsten Strootman has been with Men&Mice for many years. He is the trainer for many of our renowned training classes that we offer, as well as a resource for technical and developmental processes that we have within the company on our products. So without further ado, let me introduce you to Mr. Karsten Strootman.
Thank you, Mark. Hello, everybody. Good morning, good evening. My name is Karsten Strootman, and as Mark already told you, I'm a teacher and also member of the Men&Mice services team. So, and today I'm here for this webinar about fragmentation attacks. And these fragmentation attacks is a new kind of attack that was first described and shown during the ITF meeting in Berlin in August this year. And it's a new attack, and interestingly, it works the best in situations where DNSSEC is already deployed on an authoritative server, that is, where a DNS zone, the data is already secured by DNSSEC, but the receiver, the recipient, is not checking the data, is not validating the data. This attack, which we will see in more details on the next slides, works with fragmented data. It works on IPv4 only, as far as we know today. So IPv6 is also a way to mitigate this problem. A key component of this attack is that it requires a very large or a fairly large DNS answer. So the attacker might need to find some large text record or SPF or DKIM or anything that is DNSSEC signed in the DNS to launch this attack. This attack now then works especially well with what we call a permissive DNSSEC resolver, which is a caching DNS server that doesn't have DNSSEC validation enabled, but can do DNSSEC. So it while requesting information from the DNS system, it sends the so-called DO flag, DNS OK, to request DNSSEC data. It's also common to see clients that fall back to these non-DNSSEC resolvers, like clients that have, for their very first resolver in their TCP/IP configuration, have a DNS caching server that does DNSSEC validation, but then if that server indicates a security problem by sending back a server fail response, then that client will just go to the next configured DNS server, which then doesn't do DNSSEC, and the malicious information comes through. And according to a research from Jeff Houston from APNIC, these situations are fairly common. So first, let's have a look on how this attack works. We see here in this picture, in the lower right corner, a DNS client system that sends first a web page request to a web server under control of the attacker. Now, how the attacker manages to get this client machine to go to the website is not specified here. There are many ways how that can be done by sending spam emails or social engineering or other ways. What's important is that this client is sending an HTTP request to the web server from the attacker, and that web server sends back a web page, and that web page contains information like image links or similar object links that will require a DNS lookup, and that DNS lookup will result in a fairly large DNS answer. So that is what we see here. The client is now sending a DNS lookup for some object in the web page towards the caching name server in that organization. And both the caching name server on the left side, lower left side, and the client on the lower right side are in a local network behind a firewall and behind network address translation. The caching server takes the request from the client and does an iterative name resolution and ends up with the authoritative server, which is here on the right side, the mybank.com authoritative server. That is the server, the normal DNS server that would send the answer to that query. Now, that answer is fairly big. So in DNS, an answer can only be one UDP package. That's a limitation of the DNS protocol. And if the package is too big for the transport path, the underlying transport protocol, which is UDP in this case, needs to chop up the UDP package into multiple parts called fragments. Or what's happening here is fragmentation. And the first part, the first fragment, is being sent back to the caching name server. And then at the same point of time, the attacker will also send fake second parts, that is part number 2 fragments, to the caching name server. Now, how does the attacker knows where to send these fragments? Now, the attacker can find that out by running his own DNS server and triggering the caching server beforehand to send a request to a DNS server under control of the attacker, finding out the IP address and also the port numbers the DNS server is running on. So the caching server will receive fake fragments from the attacker, and also there will be a good fragment part 2 coming from the authoritative name server. But if the attacker is sending quick enough, then possibly the wrong answer sent by the attacker will be taken as the correct answer by the caching server and will end up in the cache. And then later on, if the client or any other client in that network wants to look up the website for mybank.com, a record, that request goes to the caching server, and the wrong information is pulled from the cache and is sent to the client, and the client is then redirected to the web server of the attacker. And there could be that the attacker is running what's called a farming website and is collecting credit card information or similar stuff like passwords. So here we see the DNS answer and how this attack really works. The green part is the first fragment, and the first fragment contains all the random bits that makes it difficult to spoof DNS traffic, DNS answer traffics. And because that is coming directly from the authoritative server, the attacker doesn't need to spoof and change anything there. This contains the answer section with the large record. In this case, it's an SPF record with information about the permitted email senders of that domain. It also includes the authority section, which points to the authoritative name servers called ns1 mybank.com and ns2 mybank.com in this case. And then the red part below, that is the fake fragment number 2 the attacker is sending. And here in the additional section, we see the IP addresses of the authoritative name servers for mybank.com. And the IP addresses being seen here are wrong, are the IP addresses of DNS servers under control of the attacker, and the time to live is relatively high, so that this wrong malicious information will be kept in the cache for a long time. So this attack is possible because the only random bit that the attacker needs to guess is the fragmentation ID. And on some operating systems, namely Windows and FreeBSD, these fragmentation IDs are very easy to guess because they are incremental. So they start with number 1, then the next one is number 2, and number 3, and number 4, and so on. It is a little bit more difficult on other operating systems, as the initial fragment ID is randomly chosen and being incremented from there. So what can we do to guard a caching DNS server against these kind of fragmentation attacks? The best solution is to deploy DNSSEC validation on that caching server in non-permissive mode, meaning the caching server really checks the DNSSEC data, does full validation, and if the data doesn't add up, if the signatures doesn't fit to the data being received, then the DNS server must discard the information and not send the data back to the client or not put the data into the cache. It also helps to deploy IPv6 because UDP fragmentation works a little bit different in IPv6 than it does in IPv4. So this same fragmentation attack is not possible in IPv6 networks. Of course, doing both would be the absolute optimum. So now I would like to show you what we can do to implement DNSSEC validation very shortly for Microsoft DNS and for the bind name server. And we later have some references for other name servers as well. But first, here are some references on the background of this attack. The original paper was presented in ITF 87 in Berlin in August this year, called DNS Cache Poisioning, New Vulnerabilities and Implications, or DNSSEC, The Time Has Come. You find the link here, you can read the paper. And there was another presentation in October this year on the DNSORG meeting. And on that meeting, 2 independent teams have verified that this attack is indeed possible. The original paper was only a theoretical paper describing the attack, but the authors of that paper hadn't tested it really. And on the DNSORG, there were 2 teams that have tested the attacks, and they found out that it is indeed possible to launch this attack. So let's take a quick look on DNSSEC validation. Here we see a DNS packet. And for DNSSEC validation, there are 2 flags important and another flag in the so-called EDNS0 section. So the flags in the header that are important are the AD flag and the CD flag. And the AD flag is what we would like to see every time. AD means authenticated data. And if we see an AD flag in an answer, that means that a validating caching name server has validated the information, has checked all the signatures against the public keys and all the public keys against the delegation signer, and the whole chain of trust that DNSSEC provides was traced back to a trust anchor that was configured. So if we see the ID flag, we are certain that the data was correct and was not spoofed. There's another flag that controls DNSSEC, which is the CD flag. CD stands for checking disabled, and that can be sent from an application towards a caching server, indicating to the caching server that the application itself would like to do all the checking, and the caching server does not need to do it. We will see in one of the slides that there are plugins for popular browsers, web browsers, that actually do this checking. So they send these applications and send checking disabled. And in the EDNS0 section, we have the DO flag. And the DO flag is the flag that indicates towards any DNS server that the recipient can understand DNSSEC, so that if there are DNSSEC information available, then the server is permitted to send that. So on the next slides, we have just the document, the information that I've just told you. So I'm going over this explains the AD, CD, and DO flags. And here we see all these flags, or not all of them, at least the AD and the DO flag in the output of the dig command. The dig command is the tool of choice if you work in a modern DNS environment, because it understands the DNSSEC extension to the protocol. NSLOOKUP doesn't do. So if you are used to NSLOOKUP in the past, it might be a good idea to look into the dig command and learn a little bit how dig works. If we do a DNS lookup with dig command like it is done here, the request was for ripe.net, a record, and with plus DNSSEC setting the DO flag, we see the answers coming with an AD flag, meaning that the DNS server here that was answering actually did validation and the data was correct. So what DNS servers we can use to do DNSSEC validation? There's bind9, and the best, not the best, the first version to do DNSSEC validation in the internet is bind96 ESV. ESV stands for Extended Support Version. Now 9.6 ESV is still available, but it is end of life in either January or February next year. So if you want to start with DNS validation, I recommend to start with one of the newer versions, and the latest versions being bind 994. And then there's Unbound, which is a fast caching only DNSSEC capable resolver. There's a recursor from PowerDNS that can do DNSSEC, and Windows 2012, including Windows 2012 Release 2, also contains a DNS server that can do DNSSEC validation. There are also some web pages that you can just use to test whether you are already in a network that has DNSSEC enabled. One page is dnssec-or-not.org. And if there's no DNSSEC, you see Captain Picard in agony, like you see it here. And if you have DNSSEC and the caching name server is doing the validation, you see a different picture, and it's like your homework to find out what picture you will see. Another web page that I can recommend for testing DNSSEC validation is from our colleagues in the Netherlands, sidn.nl. That is the organization running the .nl top-level domain. And they have this DNSSEC test.sidn.nl website, where you can click on the Do the Test button. And if you are protected, you see the green check mark. And if you are not protected by DNSSEC, you see some additional information how you can deploy DNSSEC in your network. And there is a graphical tool, part of the DNSSECtools.org website called DNS Check, that you can use to test your local DNSSEC caching resolvers. And we have a picture here. So you type in the IP addresses, or the tool will automatically read the IP addresses of the caching servers from your local computer's configuration. And then it tests the different functions required to do DNSSEC validation, like it checks for the DO flag, the AD flag, and all the different record types that are required for DNSSEC. And then if some function doesn't work as expected, it will show red, and you can click on that button to see additional information, what is failing. There are DNSSEC add-ons for the major browsers, namely Firefox, Google Chrome, and Microsoft Internet Explorer, available from www.dnssec-validator.cz. That is from the Czech Republic top-level domain. And if you install these add-ons on your browser, you see a key symbol next to the URL bar. And if that key symbol goes green, that means that the DNSSEC data was validated and was correct. If it is yellow, meaning that means that there is DNSSEC, but there's no trust anchor. So it is there's DNSSEC there, but it cannot be checked. It might be good or it might not be good. If it goes red, then the DNSSEC data is wrong, and maybe some cache poisoning attack happens just now. And if it goes gray, that means that the DNS data out there is not DNSSEC signed at all, so DNSSEC validation is not possible. But having this add-on in a browser really helps to quickly check whether DNSSEC validation works in your environment. And now I give a short overview on how to enable DNSSEC validation on both Windows and on the bind name server on Unix. Now on Windows 2012, everything is there to do DNSSEC validation, including the SHA-256 algorithm and NSEC3 resource record type support. Windows 2008 and older version unfortunately lack these functions. They only support SHA-1 and the NSEC record, which is not enough to do validation in the internet. But if you already have Windows 2012 server, you are good to go. And if you still running older versions of Windows server, you might decide to maybe just upgrade your DNS servers to get DNSSEC validation. To enable DNSSEC validation in the properties of the Windows 2012 server, you go to Advanced Enable DNSSEC Validation for Remote Responses, just the check mark. That is step number 1. And step number 2 is to download the trust anchor for the root zone, which is easily done from the command line. You open a command line window and you enter DNSCMD /retrieve root trust anchors, and that command will go out and fetch the root trust anchor from the IANA's web page, and it will do so in a secure way using SSL encryption and checking of the certificates. And once this is done, your Windows 2012 caching server will do DNSSEC validation, which you can then test out with tools like Dig or with one of the browser plugins or one of the websites. Here you see the PowerShell window with the DNSCMD command in there. So it's just calling this command. There is a question if we really want to download the trust anchors and install them. We say yes, and after that is done, the server is secured. Now we look on the Bind9 side, and support for DNSSEC validation is different from Bind versions. The oldest version that supports the new style of DNSSEC is 9.6, and 9.6 doesn't have any built-in trust anchor, and it doesn't have support for the automatic rollover of these trust anchors. That is important for next year because the DNSSEC keys in the internet root zone will be changed sometime next year, and it is recommended to have a DNS server running at that point of time that automatically can detect that change and will download the new trust anchor. If you still have Bind9.6 running by then, you have to just fetch and install the new trust anchor manually, which might be a source of a failure. So I will recommend to use some of the newer versions like Bind9.7, which supports the automatic update of the trust anchors, or even better 9.8, which comes with the trust anchor already built in, but just validation not enabled. You just have to enable validation in the config file, which we will show in the next slides. Or even the best solution is to go to Bind9.9, which comes with a built-in trust anchor and has DNSSEC validation enabled by default. So just by installing Bind9.9, you are already fully secured without the need of doing anything. Just install the software. If you are on any of the older versions of Bind, that is Bind9.8, 9.7 or 9.6, you would like to download the trust anchor. And this is the command how to do it using the dig command again. Sending a request for a DNS key resource record to one of the root name servers, grabbing for the flag 257, which selects the key signing key, and we write that into a file called root.key, which will then contain the public key signing key of the root zone that we will use as a trust anchor. However, if we just use dig to download that trust anchor, that is not secure, because while we're doing that, an attacker could spoof that answer and can send us a wrong trust anchor. So we should always double check and verify the key material received. The IANR, which is the organization publishing the root zone, also publishes the delegation signer fingerprint on a high HTTPS secured website that we see on this slide. It's data.iana.org/rootanchors/rootanchors.xml. And there we see the digest field, which is the fingerprint of the root's key signing key. And we can compute that fingerprint from the data that we have downloaded and compare that with the data on this website. And if the data is the same, then we are certain that we have downloaded the correct root anchor. And here's how we compute the fingerprint from the downloaded file. We use the command DNSSEC-ds from key -2 for selecting the SHA-256 hashing algorithm, and we apply that to the root.key file that we just have downloaded. And the tool will print out the fingerprint, and we compare that with the fingerprint on the website, and we'll see it is actually the same. The command DNSSEC-ds from key is part of the bind distribution, and if you install the bind DNS server on your Unix system, you should have that command available. If we run bind96 ESV, we then configure the content of that file as a trusted key in our named.conf file, as it's shown here. You can directly, if you like, take the data from the slide and copy that in your named.conf, but be certain to compare that first with the downloaded root.key. The key material actually should be the same. On bind97 or later, it's not a trusted key, it's a managed key. The difference here is that a managed key will automatically update it if the key changes in the root zone, which will happen next year. So it is the same information, just the name of the block is different, and there is the text initial -key between the name of the zone and the flag field, the 257. And the last step is to enable DNSSEC validation. That is being done in the option block. Two entries here are necessary. The first one is the DNSSEC enable, which enables DNSSEC as a function, and the second one is DNSSEC validation, which enables then the validation part. DNSSEC look-aside auto is also nice because that enables support for the DNSSEC look-aside validation registry, which is required for some domains that are not secured by their parents, but by the so-called DLV registry. Once we've done that, we can check which root anchors we have. There is a new command for the RNDC, the remote name daemon control, that can be used to inquire information from the bind name server. And the command RNDC segroots writes a file called named.segroots, which contains information about the trust anchors of that bind name server. And you should see at least one entry for dot, which is the root zone, algorithm RSA SHA-256, and the ID number of the key is 19036, which is the current root key. And that number and that key will change next year. And you can then turn on validation globally with the command RNDC validation on. Validation should also be on after restart of the bind name server. If for some reason you have to temporarily turn off validation of your name server, you can do so by RNDC validation off, then RNDC validation on turns it on again. So here we have additional information that you can use to deploy DNSSEC. There's a very good white paper from SurfNet, which is the university network organization in the Netherlands. They have issued a white paper containing detailed information how to turn on DNSSEC validation on Windows 2012, on bind name servers, and on Unbound. Men&Mice has published a bind9 configuration template for validating caching only bind9 server in our knowledge base that you can see here. Men&Mice also provides free installation packages of bind994 for Linux operating systems, that is Red Hat, Debian, Ubuntu. It should also work on SUSE, CentOS, and for Mac OS X and for Solaris operating systems. And if your operating system is not on this list and you would like to have also installation packages, just let us know. Send an email to support@men&mice.com and we are able to do this. And we have a blog post in the Men&Mice blog that also describes in more detail how to enable DNSSEC validation on the Windows 2012 server, which you will find the link here on this site. And this concludes my slide deck for this webinar, and we can now open the question and answer part. Back to Mark.
Thank you, Karsten. Thank you for the very informative presentation. We do have some time available now for some questions, and we do have some questions coming in. If you have a question, feel free to use the chat function to ask your question, and we'll have Karsten answer them. Here's one from Steve. Karsten, how does this solution interact with the legacy DNS infrastructure?
The DNSSEC validation is designed to work with a legacy DNS infrastructure in that way that only the DNS server, the caching name server, needs to be upgraded to understand DNSSEC. All the clients, all the machines that request DNS information don't need to know anything about DNSSEC. So the client send the query towards the caching server, and the caching server requests the data from the internet. The data coming back from the internet is then validated by the caching server, and if it is good, it is given back to the client. If the data is being seen as bad because of an attack, the caching server will drop the data and will just send an error message to the client, and that error message will be server fail. So the legacy client is guarded to receive wrong information by the caching server.
Okay, thank you, Karsten. If that answers your question, Steve, if not, I should say, please type in another question or additional information. Here's one from Brian. Karsten, would DNS over TCP prevent the fragmentation attack?
Yes, actually it would, and there is quite discussion in the ITF about if DNS over TCP would be a solution for this problem and a couple of other problems that exist in DNS in regards of spoofing. However, DNS today works over UDP because of the speed. DNS today over UDP is very quick because it's just one query packet out and one answer package in, while with TCP, it's always first a 3-packet handshake, building a session, then the query going out, answer coming back, and then the session has to be turned on. So that is much more packages and slower, and nobody really knows what impact that would have on the DNS infrastructure and on the speed of the internet in general. So probably it will solve the problem. However, it will make web browsing and other stuff that we do on the internet will make it much slower. So the people in the ITF are careful here to first test it out, and maybe it will be a solution or maybe not. We don't know.
All right, thank you, Karsten. Here's another one from Peter. If there's not enough room for data in one UDP packet, doesn't DNS go over to use TCP?
Yes, it does. However, the definition of enough room is the crucial part here. The original DNS specification from 1983 had a limit of 512 bytes per answer, and if the data is larger than 512 bytes, then TCP was requested, and that was done actually to prevent fragmentation, actually to prevent these kind of problems that we now see. However, in 1998, around that time, the maximum transfer unit in the internet was larger than these 512 bytes, and the technical community decided to relax that that limit towards 4096 bytes of permitted answers over UDP. Now, 4096 bytes is larger than the average maximum transfer unit that we see today, which is roughly 1500 bytes that we see the Ethernet MTU. So there is nowadays a risk that an answer gets fragmented on the way because of these permitted larger answers. Nowadays, only if the answer is larger than that 4096 bytes, TCP is being used. Actually, it's a little bit more complicated because client and server can also negotiate different sizes in the eDNS0, but roughly is that 4096 is the limit today, and that's so large that fragmentation on the way can happen and will happen.
Okay, thank you, Karsten. Here's a follow-up from Steve on his previous question. It sounds like you're saying that even if DNSSEC, or even with DNSSEC, if the authoritative name server doesn't use DNSSEC, the attack is still effective.
Yes and no. This attack works with large DNS answer packages, and DNSSEC signing a zone by its very nature is creating large answers. So if the remote site is not DNSSEC signed, the danger that this specific attack will happen is less the case than with, let's say, domains that are already DNSSEC signed. However, other attacks are then possible. The ironic thing here is with this kind of attack that if there is a domain out there that is already DNSSEC signed, but the caching server receiving the data does not validate, then this kind of fragmentation attack is very much possible. And we see today that most of the top-level domains are signed, and all the new top-level domains being deployed just now have DNSSEC enabled. It's mandatory for all new top-level domains. And a lot of second-level domains are also already DNSSEC deployed. So for someone operating a caching server, it gets dangerous not to enable DNSSEC. And also enabling DNSSEC validation on the caching server is low risk. There's nothing really that can go wrong there, or not much that can go wrong. And it's very easy to do, as we have seen. It's just implementing the trust anchor and turning it on. So I would say there's not much reason not to do it.
Okay, and also from Steve, wouldn't DNS amplification attacks be even more effective using DNSSEC?
DNS amplification attacks are a problem, and they are a problem with DNSSEC signed data, but they are also a problem without. And we see in the last couple of months that all the amplification attacks, at least that I have seen and I've been noticed from, haven't used any DNSSEC signed zones. Instead, they've used some other zones that were not DNSSEC signed, but still had large answer packages there. because you can find large answers, large resource records, text records, SPF records, DKIM records, other key materials being stored in DNS that create large answers. So the amplification attack is a problem, but it's not a problem that is caused primarily with DNSSEC, and it shouldn't be an excuse to not deploy DNSSEC, because not deploying DNSSEC will not make the amplification attacks go away. For amplification attacks, we have different mitigations, like we have this response rate limiting that we covered in one of our previous webinars.
Okay, looks like we have a couple more here. Still have a few more minutes. From Edgar, we're forwarding our DNS request for the public Google DNS. Are we also vulnerable?
Yes. First, Google's public DNS is doing half DNSSEC validation today. Half means if the data being received is good DNSSEC data, Google sets the AD flag, indicating that the data is good. However, as of today, if the data is bad, Google still gives the bad data out back to the client, which enables cache poisoning attacks. So the reason why Google is doing this is because they are running the DNSSEC validation in testing mode currently, in permissive mode. So they want first to figure out how much badness is out there before they enable that. I have no information when they enable that, but as of today, Google DNSSEC is not securing these kind of requests. And also, if you use Google DNS, you have to see that the data after being validated by Google is being sent over an insecure network, that is the network between the Google DNS server and your network, which again enables an attacker to do any kind of attacks against the DNS data sent there. A good solution would be to have a secure tunnel towards the Google DNS, like an IPsec tunnel, but I'm not aware that that is possible today.
Okay, very good. We have one more here, Karsten, from Olav. Would DNS curve stop this attack?
Yes, kind of. I mean, DNS curve is a DNS security mechanism to secure the transport way, and it would prevent someone from outside to send spoofed fragments over that are not signed. So yeah, DNS curve would probably help in this case. And I see DNS curve as a good addition to DNSSEC. So because DNS curve prevents some kind of attacks like this one, but it doesn't catch some other attacks that DNSSEC catches. So having both DNSSEC and DNS curve deployed would be the best solution. DNS curve is a rather young technology today. It's not an internet standard. It might become an internet standard in the future. I don't know. So yes, it is probably not a bad idea to deploy DNS curve together with DNSSEC.
Okay, thank you. Here's another one from Kevin. Would DNS cookies help in this situation?
Yeah, DNS cookies is DNS cookies, to explain, is a way currently discussed in the ITF to also make it more difficult for attackers to send false information, to do spoofing. And the idea here is the sender, the party that is sending the DNS request, will generate some random data and send that in the request, and that random data needs to be echoed back by the authoritative server. And the idea here is that the attacker cannot know that random data, so the attacker cannot send that random data in the request. So that would prevent this kind of attacks if the random data would work as a kind of a signature across the whole DNS package. I'm not entirely sure if the current draft on DNS cookies work that way. If the DNS cookies would just be like in the eDNS 0 section, it would be just happening in the first fragment and not in the second fragment, and the same attack would be possible. So my answer would be maybe. I have to look into the ITF drafts to see how DNS cookies would be implemented. But again, DNS cookies is a technology that is not here, it's not implemented, and DNSSEC is. And why wait for some future implementation of a security technology when we have one called DNSSEC already available and waiting to be deployed?
Okay, well, I think that concludes the questions. It looks like we covered them all. Yes, indeed. All right. Well, thank you very much, Karsten, and thank you all for attending today's session. It will be available on our website. The slides and the video will be available shortly through by going to our website, and then we will also be having future webinars in the future, obviously, to cover some other topics, so keep your eye out for those. With that being said, this will conclude today's web session. Thanks for attending, as I said, and we look forward to seeing you in another upcoming webinar. From Men&Mice, we wish you a good day, good evening, and happy holidays.
Thank you, Mark. Goodbye to everyone.